Hi everyone. In this video, we're going to talk about the derivatives of exponential functions, and then later we'll talk about the derivatives of logarithmic functions. Now, I do want to remind you that exponential and logarithmic functions are inverse functions. All right, now we're going to start with the derivative of e to the x. This is an exponential function where the base is e, and remember e is just an irrational number. It's approximately 2.72, just like pi is approximately 3.14. So to find the derivative of e to the x, we're actually going to go back to the definition of the derivative as a limit. So remember that we can determine the derivative by finding the limit as h approaches 0 of f of x plus h minus f of x all over h. So if f of x equals e to the x, then this limit would become the limit as h approaches 0 of e to the x plus h power, because remember, to find f of x plus h, we're just going to replace x in the function with x plus h. Okay, minus f of x, which is e to the x, all over h. Okay, now to evaluate this limit, we're going to start with properties of exponents. So the e to the x plus h power, we can actually rewrite that as e to the x times e to the h power. Because remember, when we multiply powers of the same base, we add the exponents. So this is just going backwards. Okay, minus e to the x all over h. Then we can factor out an e to the x from the numerator. So then we'll have the limit as h approaches 0 of e to the x times e to the h minus 1 all over h. Okay, now because we are evaluating the limit as h approaches 0, the e to the x is actually a constant multiple. So we can use the constant multiple law that says that we can move the constant multiple in front of the limit. So this now becomes e to the x times the limit as h approaches 0 of e to the h minus 1 all over h. Now to evaluate the limit as h approaches 0 of e to the h minus 1 over h, we're just going to look at the graph. So this is actually the graph of e to the h minus 1 all over h. So you can see as x approaches 0 from the left and from the right, y is approaching 1. So the limit as h approaches 0 is equal to 1. Okay, so let's go back. So now this would become, since we now know the limit equals 1, this just becomes e to the x times 1, which equals e to the x. So I always say this is the easiest derivative rule to remember, because the derivative of e to the x is e to the x. It's the same thing. Okay, let's look at some examples. Now, remember that even though we are adding an additional rule, which is the derivative of e to the x is e to the x, we're still going to be using all of our other rules: power, product, quotient, chain. And you remember, we've already added the derivatives of the 6 trig functions and derivatives of the 6 inverse trig functions. Okay, So in our first example, we have y equals 2 times e to the x. Now, in this case, the 2 is a constant multiple. So you can just bring the 2 down and multiply it times the derivative of e to the x, which, remember, is e to the x. So the derivative of 2e to the x is actually still 2e to the x. Okay, in the second example, we have y equals e to the 4x power. Now, in this case, we're going to have to use chain rule, okay, because the 4x has been plugged into x, so it's a composition. So we're going to start with the derivative of e to the 4x, which is e to the 4x, but then we're going to multiply times the derivative of 4x, which is 4. And then usually we'll put that 4 in front of the exponential expression, so that way, you know, we don't need the parentheses or like the dots for multiplication. So the derivative of e to the 4x power is 4 times e to the 4x power. And again, we use chain rule there. All right, just to show you some examples where we use some additional rules. If we want to find the derivative of x squared times e to the x power, then we would have to use product rule because we're multiplying two functions. X squared is the first function, e to the x is the second function. Okay, so remember, to find the derivative, we take the first function times the derivative of the second function, and remember, derivative of e to the x is e to the x, plus the second function times derivative of the first function, derivative of x squared is 2x. Okay, so just dropping some of the parentheses, this is what we have. We have x squared e to the x plus 2x e to the x. Okay, now remember, for us, simplified form is factored form. So I'm noticing that out of each term, we could factor out an x, and we can also factor out an e to the x. So factored form, if we factor out x e to the x, that would leave, from the x squared times e to the x, that would leave an x, plus, and then in our second term, if we factor out x times e to the x, that'll just leave a 2. So in factored form, we have x times e to the x times x plus 2. Okay. In our next example, we're going to have to use quotient rule because we have a quotient. It's 2 times e to the x divided by e to the x plus 1. Okay, so remember, quotient rule is low d high. Now the derivative of 2 times e to the x, because remember 2 is just a constant multiple, is still 2 times e to the x. Okay, minus, so we have low d high minus high d low. Now derivative of e to the x, remember, is e to the x plus, and then the derivative of 1 is 0. Okay, all over low squared. Okay, now it looks like we can do a little bit of simplifying. I'm noticing we can definitely factor out a 2e to the x from each term in the numerator. So if we factor out a 2e to the x from each term in the numerator, you know, then those are going to go away. So that's going to leave us with e to the x plus 1 minus e to the x. Now notice the e to the x's are going to add to 0, and so we end up with 2e to the x times 1, which is just 2e to the x, all over e to the x plus 1 squared. So our final answer is just going to be 2e to the x all over e to the x plus 1 squared. All right, I just wanted to show you one example where we're dealing with a trig function. So here we have e to the 4x power times sine of x. Okay, so we're going to have to use product rule because we're multiplying two functions. So the derivative, dy over dx, would equal first, which is e to the 4x, times derivative of the second, derivative of sine is cosine, plus second, times derivative of the first. Derivative of e to the 4x is going to be e to the 4x, but then times 4, which is the derivative of 4x. So that'll be 4e to the 4x power. And then we could factor out an e to the 4x from each term, and then that would leave cosine of x plus 4 times sine of x. Okay. Now, we can also find derivatives for bases other than e. So in this case, the function might be 2 to the x power, 3 to the x power, it could be 1/2 to the x power. So to write the general rule, we're just saying that we're finding the derivative of a to the x power, where a is the base. And so you'll notice that the derivative is still itself, a to the x power. But then you have to multiply by natural log of the base. So there's just one addition to this rule. All right, here's a few examples. Let me erase this so we can go through them together. Okay. All right, so our first example is f of x equals 4 to the 3x power. So to find the derivative, you always start by repeating the same function, okay? Because with the exponential functions, like the derivative is, like I always say, it's itself, okay, but then times the derivative of the exponent. So here I would start with, okay, the derivative is 4 to the 3x power. Now, because the base is not e, we're going to multiply by natural log of the base, so times natural log of 4, and then times the derivative of the exponent, so derivative of 3x is 3. Okay, now, you know, there's different ways that you could write this. We're multiplying, so order doesn't matter. We could at least bring together that natural log of 4 times 3, and if we write it as 3 natural log of 4, then at least we can drop some of those parentheses. Okay, next example, f of x equals 5 raised to the x squared power. So again, to find the derivative, you always start with the same function. Okay, times, this time I'm going to go ahead and do derivative of the exponent. So times the derivative of the exponent, derivative of x squared is 2x, but then also times natural log of the base, and the base is 5. So our derivative is 5 to the x squared power times 2x times natural log of 5. All right, just a few more examples. Here we have y equals 7 raised to the 4x minus x squared power. Same idea. To find the derivative, you start with the same function. Okay. Times the derivative of the exponent, so derivative of 4x is 4, minus derivative of x squared is 2x, And then don't forget the times natural log of the base, and the base is 7. Okay, our next example, we have y equals 16 raised to the sine of x power. So again, to find the derivative, we'll start with the same function, 16 to the sine of x power, times the derivative of the exponent, sine of x. So derivative of sine, remember, is cosine. Okay, and then times natural log of the base. All right, so those were all examples of finding the derivative of exponential functions. So now we're going to move into finding derivatives of logarithmic functions. And remember that these are inverse functions. So first of all, the rule, your new rule is the derivative of natural log of x is equal to 1 over x for x greater than 0. Now, first of all, why do we have the x greater than 0? That is because, remember, we can only evaluate logarithms for values greater than 0. Okay? Now, where does this rule come from? Well, remember the rule that we learned when we were finding derivatives of just inverse functions? So these were problems that would say if f and g are inverse functions, you know, find g prime of x, and we knew that that would equal 1 over f prime of g of x. Okay, well, in this case, we're saying that f equals e to the x, which means that g of x, the inverse, would be natural log of x, because these are inverse functions. Okay, so to find g prime of x, it would equal 1 over f prime of natural log of x. Well, if f of x equals e to the x, remember we just learned that the derivative of e to the x is e to the x. So then if I find f prime of natural log of x, which means I'm going to replace x with natural log of x, then e to the natural log of x, they're going to undo each other, and that's just going to equal x. So this now is g prime of x is now equal to 1 over x. And so that's our new derivative rule. The derivative of natural log of x is equal to 1 over x. Okay, examples. So in our first example, we have y equals the natural log of 4x. So again, we're going to have to use chain rule here because the 4x has been plugged into x. So it's a composition. So the derivative, I would still start with, whenever you're evaluating natural log, you're always going to start with 1 over what's in parentheses, okay? So 1 over 4x, but then times the derivative of 4x, which is 4. Now, it's kind of interesting what happens here. If you multiplied straight across, you would just get 4 over 4x. But notice, that just simplifies back to 1 over x. So the derivative of natural log of 4x is still 1 over x. Okay, let's look at number 2. We have natural log of x squared minus 3. So the derivative is going to equal 1 over x squared minus 3, but then times the derivative of x squared minus 3, which is 2x. And that would be like 2x over 1 as a fraction. So when you multiply straight across, we'll get 2x over x squared minus 3. So you guys, as you can see, you basically end up with the derivative of the inside over the inside. So like for number 3, honestly, once you get the hang of these, you could just go right to the final answer. We're deriving natural log of 3x squared minus 5x plus 8. So I know the numerator is going to be the derivative of 3x squared minus 5x plus 8, which is 6x minus 5 over 3x squared minus 5x plus 8. Because that's what would happen if we did 1 over 3x squared minus 5x plus 8 times the derivative. Okay. All right. Number 4 real quick. Natural log of the square root of x. So again, we're going to start with 1 over the square root of x, but then times the derivative of square root of x. And remember, that ends up being 1 over 2 times the square root of x. And so if we multiply straight across, we'll just get 1 over 2 times, well, square root of x times square root of x is just x, because the radical goes away. All right, just a few more examples to show you how, again, we can bring in some of our other rules. Number 5 is an example of product rule. So to find the derivative of x squared times natural log of x, we would use product rule. So it would be first times derivative of the second. Remember, derivative of natural log of x is 1 over x, plus second times derivative of the first. Derivative of x squared is 2x. And then we can simplify because x squared times 1 over x just simplifies to x. And then in our second term, I'd probably just put the 2x in front of the natural log of x. And then you might also see it factored. We could factor out an x from each term, which would leave 1 plus 2 times natural log of x. Okay, number 6 is an example where we have to do quotient rule. So the derivative would be low d high, which is 1 over x, minus high d low, derivative of x is 1, so I'm not even going to write that, all over low squared. And then x times 1 over x is just 1. So in the numerator, we end up with 1 minus natural log of x all over x squared. Okay, let's see what happens when we flip that around. Now we have x divided by natural log of x, but again, we're going to use quotient rule. So we'll do low d high, which is 1, minus high d low, which is 1 over x. Okay, all over low squared. So that'll be natural log of x squared. Okay, now remember x times 1 over x is just 1. So we end up with natural log of x minus 1 in the numerator all over natural log of x squared. Okay, number 8 is an example of chain rule because we have natural log of x raised to the 5th power. So when we use chain rule, we're going to bring the 5 down in front, keep the inside the same, subtract 1 from our exponent, but then multiply by the derivative of the inside, which is 1 over x. And then we can just multiply straight across, and we'll get 5 times natural log of x to the 4th power all over x. Okay, number 9 is another example of chain rule because remember, anytime we have a radical, we're going to convert it to a fractional exponent. So the square root will convert to the 1/2 power. And then when we find the derivative, we'll bring the 1/2 down, keep the inside the same, subtract 1 from the 1/2, and then we'll multiply by the derivative of the inside, which is 1 over x. So then this will end up equaling, so this one is interesting because we have the natural log of x to the negative 1/2 power, so we're going to move that to the denominator, and see how the 2 and the x are already in the denominator? So we'll just be left with a 1 in the numerator, and then a 2 times x times the square root of natural log of x. Okay, number 10, we have cosine of natural log of x. So again, this is actually chain rule, or you could think of it as ETA. If you think of it as ETA, we can skip the E part because cosine is only raised to the 1st power. So to find the derivative, we'll go right to finding the derivative of cosine, which remember is negative sine, but you'll keep the inside the same, which is natural log of x, but then you'll multiply by the derivative of natural log of x, which is 1 over x. So when we multiply straight across, we'll just get negative sine of natural log of x all over x. All right, now number 11, this is just switched around now. We have natural log of cosine of x. So when we find our derivative, we'll say, okay, derivative of natural log of cosine of x, remember, is 1 over cosine of x, but then times the derivative of cosine of x, which is negative sine of x. And then if we multiply straight across, we'll get negative sine of x over cosine of x. And actually, we could simplify this by using one of our trig identities. Sine over cosine equals tangent. So we could say that this is just equal to negative tangent of x. All right, number 12, we have y equals natural log of x. So again, this is chain rule. So we'll start with the outside. So we'll start with 1 over natural log of x, but then times the derivative of natural log of x, which is 1 over x. And then just multiply straight across and we get 1 over, and I'd probably just put the x in front of the natural log of x just so it's not confusing. And that would be our final answer. All right, you guys, here I wanted to show you that you can use the properties of logarithms to help you take the derivative of some more difficult expressions. And by the properties of logarithms, I'm talking about how we can expand and condense logarithms. So hopefully these look familiar. Remember, if you're finding the logarithm of a times b, that equals log of a plus log of b. If you're finding log of a divided by b, remember that expands into log of a minus log of b. And then if you have log of a raised to the b power, you can bring that exponent down in front and multiply it times the logarithm. So we use these properties to either expand logarithms into a sum or a difference, or we can also use these properties to condense logarithms into a single logarithm. But they can also be helpful when we're finding derivatives. If you look at example 13, we have y equals the natural log of the square root of x squared plus 2x minus 3. So again, like always, we're going to convert that square root to the 1/2 power. But then we could use this property, bring the 1/2 down in front, and multiply it times the logarithm. So now, when we find our derivative, it'll be a lot easier. So now y prime is going to equal, well, I'm going to just put the 1/2 in front, and then I'm going to go, okay. Remember how when we found derivative of natural log, we would always start with 1 over what's in parentheses, then times the derivative of what's in parentheses. So the derivative of natural log of x squared plus 2x minus 3 is just going to end up being 2x plus 2, which is the derivative of the inside, over x squared plus 2x minus 3. Okay, now as far as simplifying goes, I'm noticing that we can do some cross-reducing with the 2's and get x plus 1 over x squared plus 2x minus 3. And I was quickly thinking, okay, if we factored the x squared plus 2x minus 3, would we be able to cancel any factors? But it doesn't look like we would, because that would factor into x plus 3 times x minus 1. But if you could factor and then cancel some factors, you would want to do that. Okay, number 14, this is natural log of x squared divided by 3x minus 2. So, you know, one way to do this would be to just jump right into the derivative, and it would be 1 over x squared over 3x minus 2, then times the derivative of that quotient, which would require a quotient rule. That's going to get kind of complicated. Instead, we can use our properties of logarithms, and we can expand this quotient. So we could rewrite this logarithm as natural log of x squared minus natural log of 3x minus 2. Then we can, because we're now finding the derivative of a difference, we can just find the derivative of each term. So derivative of natural log of x squared, that's just going to be 2x, the derivative of x squared over x squared, minus 3, derivative of 3x minus 2 over 3x minus 2. And then a little bit of simplifying, the 2x over x squared would just simplify to 2 over x minus 3 over 3x minus 2. Now, I'm just going to stop there just because the video is already a little long. But if we did go forward, we'd have to find a common denominator in order to subtract these fractions. Okay, guys, the last thing we have to look at is that we can also find derivatives of logarithms with other bases. So we've been focusing on natural log of x, which is base e. We can have logarithms with other bases. So here we're just calling the base a. So if we're finding the derivative of log base a of x, notice that the derivative is still 1 over x, but then you have to multiply by natural log of the base in the denominator. Okay? All right, just a few examples. So here we have log base 2 of 2x minus 1. So the derivative, we would start with 1 over 2x minus 1 times natural log of the base is 2, so times natural log of 2. Okay, but this is chain rule, so we then have to multiply by the derivative of the inside, which would be times 2. And then multiply straight across, and we just get 2 over 2x minus 1 times natural log of 2. All right, here we have log base 3 of sine of x. So again, to find the derivative, we'll start with 1 over sine of x, okay, times natural log of the base, but then times the derivative of sine of x, which is cosine of x. Okay, multiply straight across, and we get cosine of x all over sine of x times natural log of 3 . Okay, and here we have x squared times log base 4 of 4x. So in this case, we have to use product rule because x squared is your first function, and then log base 4 of 4x is the second function. So here we would go first, okay, times derivative of the second, which is going to be 1 over 4x times natural log of 4, because 4 is the base. Okay, times the derivative of 4x, which is 4, plus our second function times the derivative of the first function, derivative of x squared is 2x. All right, so we can do some simplifying. I mean, here the 4's are going to cross reduce. If we multiplied straight across there, we'd have x squared over x natural log of 4. And then the x squared and the x actually will simplify. I'll just do that in another step. Okay, plus over here, I'm just going to put the 2x in front of the logarithm just so we can drop some of those parentheses. And then the x squared over x, those will simplify to just x. And then I am noticing we could factor out an x from each term, which would leave us with 1 over natural log of 4 plus 2 times log base 4 of 4x. And then, you know, if we didn't want to leave that 1 over natural log of 4 just because it's a little ugly, we could either, yeah, I think I would just multiply straight across. And, oh, I'm sorry, I forgot. I factored that out of all of this. There we go. Yeah, I think I'm just going to stop there. We factored out an x, and that left us with 1 over natural log of 4. What I was thinking is we could maybe use our negative exponents. So if we flipped that 1 over natural log of 4, it would become natural log of 4 to the negative 1. I don't know if that's a whole lot simpler, but we've probably done enough, so we'll just stop there. Okay, one last example, and what I wanted to remind you of here is that when you see log without a base written, this is called the common logarithm, and it's always base 10. Okay, so we don't really write the base, it's understood to be there. But you need to know that because you'd have to multiply by natural log of 10. Okay, so our derivative here would be 1 over 2x squared plus 1 times natural log of the base, which is 10. Okay, times the derivative of the inside, which would be 4x. And then if you multiply straight across, we'll get 4x over 2x squared plus 1 times natural log of 10. So just remember, when you just see log, the base is 10. You can always add it there if you want to, but typically we won't write the base because it's understood to be a 10. Okay, you guys, that concludes the video. So we will definitely practice in class. As always, thank you for watching and have a good night.